Good afternoon, everyone. Welcome back to the ECE 590 seminar. Presenting today is our own Dr. Andrew Stillwell. Dr. Stillwell is an assistant professor in the Department of Electrical and Computer Engineering here at the University of Illinois Urbana-Champaign. He received his bachelor's in science in both electrical and computer engineering at the University of Missouri-Columbia in 2005. He spent 7 years at National Instruments before arriving at the University of Illinois at Urbana-Champaign, where he received his master's and PhD in electrical and computer engineering in 2015 and 2019, respectively. His research interests include renewable energy applications, hybrid switched capacitor converters, power electronics design optimization, high density and high efficiency power converters, and advanced control techniques for multi-level converters. Today he presents high conversion ratio DC to DC converters, transformers versus capacitors. Dr. Stillwell, you have the floor.
Okay, thanks for the introduction there, Max. All right, so high level, we're gonna talk about power converters, and specifically we're gonna talk about compact DC to DC power converters. So we're looking at kind of the cutting edge of high density, high efficiency DC power converters. And we're gonna talk about high level, how do we compare these type of solutions? Because in academia, we kind of like to be able to show off and be able to say, you know, our Kung Fu is better than so-and-so's Kung Fu. But making those comparisons in a fair way is kind of complicated. So that's one of the kind of overlying topics I want to touch on. And then when we get into that, we're going to look at kind of two high-level solutions. We're going to look at transformer-based solutions for some of these applications, and then capacitor-based solutions here. I should start off with giving credit where credit due here. So a lot of these slides are taken from Zijiao Yi. He was a former colleague of mine here at Illinois before he moved to UC Berkeley. And a lot of these slides are based off of a webinar that he gave given here, and it's a really good webinar. So if those of you that are in Pels, you should be able to view it for free still. The web link is included on there. It's just about a year old. It's an excellent presentation. He does a very good job of breaking down the operation of a really interesting power converter topology, and furthermore, he does a really good job of kind of quantifying why that specific topology was targeted and why he designed and built that converter. So if you have about an hour and want to learn a lot about switch capacitor converters and resonant converters and just good converter design, take a look at that webinar. But as I said, a lot of these slides are credit to him, so all the good stuff is his and all the typos are definitely mine. But high level, when you look at power converters right now, we're kind of riding on two different trends. There's the controllers and the switching devices. So the controllers that we have now are excellent, and they're more powerful, and they're cheap, and they have lots of capabilities. So for example, this is looking at some of the Texas Instruments microcontrollers. There's lots of PWMs, there's lots of ADCs that are built into the microcontrollers. They're fast, they respond quickly, they're reliable, and they're really cheap. So you can get very good control for very low cost. At the same time, our silicon devices are starting to get replaced with silicon carbide and GaN devices. So these wide bandgap semiconductor devices are coming in. And essentially, we're getting better figures of merit out of these devices, right? They have lower switching losses for the same type of operation, and they have lower RDS-on or conduction losses in a similar footprint. The cost isn't quite down there yet, and I'll say reliability is still an improvement, but considering how young of a technology they are compared to silicon, we're already seeing lots of inroads of GaN and silicon carbide into shipping devices. In fact, we're at the point now where you can buy kind of a laptop charger, and one of the advertising bullet points is like GaN chip inside, right? It's barely using the GaN chip, but it's still there and it's still taking advantage of it. And we're going to see that continue to sweep out into more consumer type devices. And what this means is that we have these better switches, we have this better control, and what we're trying to do is produce high power density converters, but we're still seeing that the passive volume dominates. So this is a good example of a converter from our friends at ETH. It's a very high efficiency converter. You can see down here it's about 98% efficient. And they're calling it compact, but at the same time, when you look at it, you can see most of the volume is taken up by these DC link capacitors or these inductors or a transformer. And very little of the portion of the product, in fact, if you look at basically just this area down here, is the actual control and the switching devices. So the name of the game for most of these type of converters, when we want this high power density, is how do we reduce the size of these passive component volumes. So let's go through, we looked at trends, let's look at comparing power converters. And if you look at how do we compare two power converters, it's actually very difficult. The best example is to look at something like the Google Little Box Challenge. So the Google Little Box Challenge was going on about 5 years ago now. And the idea was Google put up this challenge. They basically said, let's see if we can stimulate some research in an area. And they wanted to see how good of a power converter someone could build. And in this case, they chose a single phase microinverter. So you can think of this as something for a solar application. And they basically said, what is the best converter you can build given these set of specifications? And so it had these good, well-defined specifications. It had certain THD targets. The efficiency had to be above a certain value. It had to pass EMC. And then they also included things like temperature rise, right? It couldn't get so hot. So you actually had to take into the whole account, the whole solution. And the kind of fine competition variable was, okay, power density needs to be at least greater than 50 watts per inches cubed, but then the tiebreaker would go to the most power dense solution, right? So they're really pushing, make sure you hit these minimum specifications, which were not easy to actually hit, but let's make sure you hit those. And then we'll choose the winner from the one that has the highest power density. And then the incentive there was $1 million, and of course, fortune and glory and everything else. So what's nice about this is, with this little box challenge, is you have a box, right? In the end, you have this solution where all your power electronics, all your filters, all your control, everything has to fit in a box. And the only thing that goes into it is our DC output, and the only thing that comes out of it is our AC output. And everything in between is what we're measuring. Now, obviously here you can see the on-off switch. They didn't count that as part of the volume, and this particular solution from UIUC didn't go through great pains to minimize the on-off switch. But overall, you can see this whole solution here ended up being about the size of a deck of cards. And everything was in there, right? So whatever was in there had to work based off that DC input. It had to cool. It had to provide the control. It had to do the sensing. It had to basically regulate the converter such that it met the specifications at all times. And so this makes it really easy to compare these type of power electronics converters, right? We all know they meet these specifications, and then we really just look at, okay, how well do they meet certain other specifications? So this is looking at some of the Little Box Challenge finalists, and we can go through here and see a few things. Here is the CET Power one in blue. This is the one that, if I recall right, ended up winning, right? It had a very good power density, not super high efficiency, but it worked, right? ETH Zurich was here. There's one from Tennessee. All the rest of these going through, actually CET Power wasn't, sorry about that. CET Power wasn't the winner. I believe it was actually this triangle up here. But CET Power is one that verified the results and provided their efficiency data in a publication. And what's interesting about this, okay, here's the UIUC solution here, and you can see the power density was excellent and the efficiency was excellent, but it didn't win. And in fact, lots of these by the specifications didn't actually meet the specifications, right? When they announced the top three, basically it was, if I recall right, this one, and then the Schneider Electric, and then the Virginia Tech ones. So I'm sorry, no, we are talking about number one right here. CET Power is rated here. So they had 150 watts and about 95% efficiency. Schneider Electric was here, and then Virginia Tech was a little bit lower. And what's interesting is there were about 18 finalists, and Virginia Tech actually had the lowest power density of those 18 finalists, but they came in third. And what that tells you is that only 3 of these power converters met all of those specifications when it came to ripple, when it came to EMI, when it came to the temperature rise and everything else here. So this is a great equalizer, right? We have this one box, everything kind of fits in there. We know how power density is being measured. It's just the power divided by the volume. we know that they're all meeting basically the same specifications. They might be exceeding the specifications, but they all at least work. And what we find in academia is this is pretty rare. We don't often have a situation where we have the exact same application that we're benchmarking against. And so comparing our converters is kind of apples to apples is very challenging, and it leads up to a little bit of interpretation. And so that's something I want you to keep in mind as we look at these next few technologies of we may or may not really be looking at something that's apples to apples when we compare these different pieces of this. So for the rest of this, I want to talk about a kind of benchmark application, and that's for data center power delivery. And with data center power delivery, you have the grid connection, you go through these AC to AC conversions, and then you go to an AC to DC. And then at some point, you get down to the bus converter, where you have kind of 48 volts maybe from your UPS, and then you step it down to 12 volts to your actual point of load servers. And this is a pretty well understood and well defined space, and there's quite a few converters out there in this space. So it's kind of a good area for us to kind of be able to benchmark converters, right? They're all looking at doing this 48 to 12 volt conversion. They're all looking at similar power levels. And in general, while they don't print it, they're trying to get to very similar ripple specs and everything else along those lines. Although again, not every publication has done a great job of saying what is the ripple spec that they're designing for. If we look at a conventional converter that we'll see in this type of application, a good example is a non-isolated buck converter. And this is one from EPC, and they kind of use this to show off their GaN devices. And it's basically an interleaved buck converter. So you can see there's these 5 interleaved stages here. Pretty good efficiency as far as that 95% efficiency. Power density is 1,000 watts per inches cubed, which is pretty high. If you compare that back to Google Little Box, right, we saw that the winner was there around 150 watts per inches cubed. But it's a different application, and we're also seeing that that's basically the efficiency of this power stage. So at a certain point, they kind of draw a box around this and say, here's our power stage. And that's the volume of that. And then we take the power that we're processing, and then we get our power divided by volume to get our watts per inches cubed. Another good thing to note is this is a switching frequency of about 500 kilohertz. So they put this out, and they're kind of benchmarking their converter against many other applications, right? So they're showing a plot here where they've got power density here on the left-hand axis, and then they got load efficiency on the right-hand axis. And of course, ideally, we have something up here that's very, very efficient and very, very power dense. So we want dots on this place that are up and to the right. That would be our ideal power converter, where it's very power dense and very efficient. So here they're showing a few different solutions, and they're showing basically how this compares to many others. And of course, they're saying, okay, we're pretty good, right? We have very high power density, and maybe not the best efficiency, but power density wise, we're looking in a nice range. And they're comparing mostly to other industry shipping products. And you might think, okay, so is this the best we can do? And in general, when we're looking at how do we decrease the size, we generally look at going to higher frequency, right? So if we look at, for example, the ripple on our inductor and look at the fundamental equations, VL is equal to L di by dt. Well, if we decrease our dt, otherwise known as increasing our switching frequency, we can shrink the size of our L and still have the same ripple on there given a certain voltage. Likewise, if we look at our fundamental capacitor equation, right? IC is equal to C dV by dt. Well, if we, again, decrease the size of our dt, we can drive down the size of our capacitor with the same ripple and all the rest of those components there. So we have an opportunity, if we just switch faster, that we'll be able to hopefully shrink the size of our converter. The challenge, though, is that on these traditional converters, that if we increase our conventional converters, if we increase our switching frequency, we also end up increasing our losses, right? So there's typically an overlap loss in a conventional buck converter, where at a certain point you have voltage across your switch and you have current flowing through that switch at the same time. And that gives you this loss, and that loss then is proportional to our switching frequency. So we increase our switching frequency to decrease the size of our inductor and decrease the size of our capacitor, but in the process, we end up increasing our losses. And this drives us to kind of more complicated topologies, right? So if we look at this on the right, this is an example of a very high frequency application, right? I believe they were switching closer to like 13.6 megahertz. And you end up having to make a lot of sacrifices, right? You change your topology pretty drastically because you can't have this high switching frequency going into a conventional buck converter. And it turns out, while these converters do reach very good conversion ratios and are able to operate at very high switching frequencies, they haven't been very successful in driving down the power density. We can see here they've got these air core inductors that end up being relatively large. And it turns out that not all of these components are completely lossless. And so there's parasitics, and those parasitics don't operate well when we're going to very high frequencies. So overall, just going to higher switching frequency doesn't turn out to be a very good solution. So instead, we have to look at better topologies and how do we better utilize the components we have. And so one way to look at this is to start with transformer-based solutions, right? What are some of the popular there? And if we start looking at transformer-based solutions, the first thing we should do is kind of look at the best and the brightest and kind of what we consider the state of the art. And this would be typically considered an LLC converter. So an LLC converter is a resonant converter. The switches operate at a 50% duty cycle. And then the primary and secondary side switches operate with ZVS. And what does that basically mean? You can see that essentially, if we look drain to source on S1 and S3, and then on this side, and then also on the synchronous resonator side, basically the voltage across the switch goes down by the time they actually turn on. So you can see the gate signal goes high and the voltage across the switch is already zero. At the same time, you can also get zero current switching on the secondary switches, which also turns into this nice behavior, where we're able to basically operate them with zero current switching as well. So we no longer have many of those overlap losses that we saw previously when it came to having a voltage and current in the switch at the same time, right? Because we have this resonant operation and because of the operation of the LLC itself, we're able to basically soft switch in most of the operating range of this converter. And so we can switch faster without having to worry about our switching losses increasing drastically. Now we still have limitations on this, right? We still have parasitics in this converter. And that's why these converters are still not operating up at, say, 13.6 megahertz or something along those lines. They're still operating with something reasonable. But now we also use this structure to provide step down as opposed to using a lot of the energy storage elements. So this transformer also gives us this way of stepping down the voltage. And essentially this is very similar to our traditional converter, right? We have some sort of chopper stage. It goes through a little bit of a step down stage with the transformer. And then we have a rectifier stage on the output. Now, if we look at kind of some of the results of this, this is what I would consider kind of one of the most recent versions from this. And this is from the group out of Virginia Tech. They've spent a lot of time optimizing this design. And they've basically not only looked at the input stage here and making sure they get soft switching, but they use this matrix transformer, which further basically allows them to decrease the burden of flux inside the transformer itself and really optimize the design of the transformer. So this is a 900 watt 4-to-1, also designed for 48 to 12 volts. It uses GaN switches so that it can switch very fast with low losses. And then it's got this interleave synchronous rectifier that allows it to basically share the output currents among multiple switches. And this is important with these type of applications because the output is at lower voltage. And so if you're at 12 volts output and you have 900 watts, you can imagine that's quite a bit of current that needs to be going on the output stage. So being able to share that among multiple switches turns out to be very valuable. And it's switching at 1 megahertz. And it's important to note that all of these switches are switching at 1 megahertz. And that's where it's very important that they maintain that zero current switching in many cases and zero voltage switching. And this has gone through many iterative designs, right? So if you look at this solution, it's a very clean design, right? Everything looks very professional on this. And it's basically the result of many dissertations and many postdocs hammering on this over the course of 5 to 10 years, right? You can go back and find early LLC papers from more than 15 years ago, And just about every power electronics conference, there's usually an iteration on this particular design. And it's usually good work, but they're really focusing on chasing down the next small little losses, right? At one point they made the switch to GaN, and that was a new paper. They introduced the matrix and transformer, and that was a new paper. They introduced lots of different optimizations to the flux paths and the layout, and that was pretty much this most recent paper. But in the end, they get this really clean design, right? This is their power stage. This is where they're drawing their box. And you can see things like the switching, the gate drivers are here. All of the capacitors are here. Here are all the switches for the primary side, and here are the switches for the secondary side. And this is a double-sided design, so you can see basically both pieces of this. And this is a custom matrix transformer that they've also gone through and done a lot of optimization for. So this is a very nice converter that has been worked in over time. You can see it looks very professionally done. This is likely machine placed when you look at how small some of those components are, or at least at the very least, I know I can't solder something and make it look that nicely by hand. So more than likely, either they've got some really excellent technicians or grad students, or they had a board house produce this. So very nice design and very good work. And they've also introduced their plot here, right? So this is their power density plot where they compare their work with other people's work. And here's a few data points here. You can see this particular point here is that EPC converter that we looked at before. And this is where EPC also talked about where their target performance was at a higher power level. And you can see, okay, this is where Virginia Tech has put their stake in the ground. Right, they've said, okay, we've got higher efficiency and we have higher power density, right? We're up here at this 1600 watts per inches cubed. Now, it's important to realize here, right? While this is a nice, very clean solution, comparing this with many of the Vicor and the shipping modules out there is not telling the whole picture there, right? These Vicor solutions typically have a wider range of specifications they need to work under. They have EMI characteristics that they have to hit, and they have to hit it very consistently. The Vicor solutions also include the control and any sort of auxiliary power, and all of that is included with that brick, right? The Vicor solutions you can think of as the Google little boxes, right? Power goes in, power goes out, everything else has to be contained in there. Whereas the Virginia Tech and many of the other academic solutions on here have basically drawn a box around theirs and said, this is our power density. And it's accurate within the context of that. But anytime you see one of these charts and they compare it to industry, you have to realize we're typically not really looking at something that's apples to apples. If you were to continue to develop on this, more than likely you would see this Virginia Tech go down and to the left a little bit when you start adding on the auxiliary power supplies and the EMC, and maybe some of the other control is included in that box. But overall, they do a good job of comparing themselves with other academia, which I think are these bluer boxes here. And then they put this note here about this particular box, right? This is a non-isolated and unregulated. And we'll take a look at this later, right? This turns out to be basically the next solution that we're going to talk about. But this transformer-based solution is very interesting, right? It takes what is relatively a conventional topology, the LLC, and they basically just iterated on it over time. They've done some nice innovations with the transformer. They've done some nice innovations with layout. They've done an excellent job of creating the board and tracing down every little loss where they've slowly over time kind of inched this plot up and to the right. But it's been very much an iterative process over time, and starting with a nice topology and a nice match, but continuing to improve. Now, if we look at some capacitor-based solutions, I think there's some interesting parallels here, but also some interesting differences that we'll see when compared to that transformer-based solution. And so fundamentally, why would we go to a capacitor-based solution? And what we found is when we look at passive components in the kind of power area that we're operating in, and that's this less than 1 kilowatt or less than 2 kilowatt space, we find that the power density of many of these capacitors is much higher than the inductors. So this is a plot of a survey that we did several years ago. And you can see in blue is plotted the energy density of all these capacitors versus the voltage rating. So our energy density is our 1/2 CV squared divided by the actual volume of the capacitor. And so you can see we're up here relatively high. Here, plotted on the same axis, we can see this is 10 to the 0 and this is 10 to the -4, very similar to here, is the energy density of several inductors that are also in that space. And we can see, again, this is also their current rating. So this would be the 1/2 Li squared divided by the volume of the inductor. And what we find is that our capacitors generally have a couple orders of magnitude higher energy density than our inductors. So if we're able to use more capacitors and less inductors in our design, then more than likely we're getting a gain in the power density of our solution, right? We're always going to need these energy storage elements in order to do our conversion. But by introducing more capacitors and hopefully reducing the size of our inductor, hopefully we're overall reducing the size of our power converter. And we're starting to see this in industry, right? So this is a design from Linear Technology. It's a 2-to-1 charge pump controller. It's at a fixed ratio of 2-to-1. It's really efficient because it's a 2-to-1 converter. But they're showing this really high power density and they're claiming it's a rugged design, which it should be a rugged design, right? Everything's surface mount and it operates. But how can we what's the best switch capacitor topology and how can we maybe design that for our 48-to-12 type application as opposed to just this 2-to-1 fixed ratio? So this is where Zichao spent a lot of his time, right? This is a cascaded resonant converter. And basically you can think of it as these two stages where you have this cascaded 2-to-1 resonant switch capacitor converter. And what's nice about it is you still get this soft charging and soft switching. And the soft charging basically means that we're not in a scenario we have capacitors discharging straight into other capacitors, which is typically a downside of switch capacitor converters, right? Every time we charge or discharge these capacitors, it's happening through an inductive element, which means it's not a lossy charge or discharge. This particular converter is a 4-to-1 fixed ratio. It's unregulated, which means we don't have an option of changing that ratio. And then again, very simple control, right? 50% duty cycle for all switches, and then it notes this extreme power density and efficiency that we'll get to in a bit. Now, one of the challenges of this particular converter is that we have this first stage, and it basically resonates. But in order for it to resonate well, it relies on basically having a very fixed voltage here on the output of it. And likewise, this second stage also needs a very fixed voltage here on the input in order for it to resonate properly and supply resonant current to the output. And what that means is typically for this type of design, if we just use it as is, you need a really large midpoint capacitance, right? That has to be much larger than C1 and C2, such that you have this stiff voltage at that point, and it doesn't participate in the resonant operation, right? Your resonant operation is only between the L and the flying capacitors as opposed to this particular capacitor operating in that resonant operation. So, but we don't want this, right? We don't want a scenario where we just put a large midpoint capacitor here. So a lot of the innovation with this design was how do we reduce the size of that midpoint capacitor? And what it turns out is the best way is two-phase interleave operation. And so essentially, if you think about it, we have these two input phases here, and we operate them in phase, and they're resonant operations. So the current going into this node, and you can see these two midpoints are tied together, which is interesting, right? Usually when we look at interleave operation, we either tie the input together or we tie the output together. Sometimes we do both. In this case, we tie the input, the output, and we tie the midpoint together. And so this would be the current that goes through here is the sum of both of these currents. And then if we look at the second stage, we operate it out of phase such that it only is delivering current during half of this. And you can see because it's a step down, but it's delivering more power or the same amount of power, it actually ends up doing the same amount of current as one of our interleave currents going in. And then we interleave the second stage at a phase shift such that it also makes up the difference here as well. And so you can think of it as if we look at the sum of all the currents into this node, we can see that the sum of all these currents is 0. So that means there should be no current flowing through these midpoint capacitors. which means that basically we've decoupled these midpoint capacitors and they're no longer operating within the in the resonant operation or interfering with the resonant operation of this particular converter. So by operating in these two stages and very carefully handling the control, we're able to operate in such a way that we can decrease the size of the midpoint capacitor. It's stiff by design as opposed to being stiff with respect to a large capacitor here. So overall, this allows us to reduce the filter size of the capacitor, and then it also allows us to have this current sharing where half our current is going through this phase and half our current is going through this phase, and that allows us to also make sure that we're sharing that current among multiple switches, which in general also provides us an opportunity to reduce the ratings of these components as well. So if we look at the hardware implementation, this actually uses silicon MOSFETs. So it is not using GaN. And it turns out that in this lower voltage space, that silicon MOSFETs, especially when it comes down to conduction losses, silicon MOSFETs are very competitive with the GaN counterparts in this space. This also uses the interleaved stages. It's just using off-the-shelf inductors, right? You can see the little power inductors here and here. And it's only switching at 100 kilohertz, right? So we talked about the transformer-based LLC earlier. It was up there at megahertz. This one's only at 100 kilohertz. And part of that is because of those silicon MOSFETs, right? They have very good conduction losses. They still suffer when it comes to the switching losses. So this design had to make the trade-off of switching a little bit slower. And then, of course, because we have this quasi-resonant and resonant operation, it has this benefit of being robust with respect to component tolerances, which basically means they're still able to get this soft switching even if there's some variance in the capacitance and inductance values. And Zichow's paper goes into that a bit more about that specific mechanic. Another alternative switch capacitor converter that's worth looking at is a switch tank converter. So this is out of North Dakota State, and this is also a 48 to 12 converter that they've done a lot of work on. This particular journal article tried to go through and do very much this analysis that we're doing kind of at a high level, right? It actually built several 48 to 12 volt converters and tried to compare them as an apples to apples converter. Their analysis is, it's good. It's missing a few components. It's interesting that they renamed the Cascaded resonant converter to something completely different while still citing the original paper. But this is an alternative topology that we can look at where, again, they've used more capacitors and more switches. There's no transformer here. They're still getting soft switching because they've introduced these inductors that allow them to get this resonant switching. And so this turns out to be a very nice counterpoint to the other operations. If we look at this particular hardware implementation, it does use GaN switches. It does use off-the-shelf inductors as well, so there's no custom magnetics there. It has about a 350 kilohertz switching frequency, so kind of in the middle of this. And again, they're using GaN switches, so it behooves them to switch faster. One thing to note, though, is that their resonant operation is actually very dependent on these well-matched components, right? So they choose some very specific technologies when it comes to the capacitors that have very tight tolerances. Same thing with their inductors. This particular topology has to operate at a very specific resonance frequency, otherwise it loses a lot of the benefits. But overall, again, a very nice hardware implementation. They also, at least in many of their cases, had these boards professionally manufactured as opposed to manufactured in the lab. Now, if we compare these, right? Well, here's our original EPC buck converter that we looked at. Here is the switch tank converter. And then here's the Virginia Tech LLC over a couple different operating conditions. And this is the switch capacitor converter that we looked at before. So this is one of Zichow's slides. So when we say this work, we really mean this is the cascaded resonant converter operating at different efficiencies and different power densities. And this line is mostly dependent on what their input voltage is. All of these are looking at 4-to-1 conversion ratios. But it turns out that if you operate this at a higher voltage, then your where you operate on this can vary quite a bit. So they can operate it at a higher voltage, and their efficiency goes down, but their power density goes up quite a bit. Likewise, they can operate this as a lower voltage, and their efficiency goes up, but at the same time, their power density goes down. Basically, what this shows is they're limited by their output current as much as anything in this case. And so they tried to at least plot this over a few different ranges. So for the most part, this is I would say, a pretty good apples to apples comparison, right? These are all converters that are academic converters. So all of them kind of draw a box around their converter and say, this is my power stage. I don't think any of them are necessarily including their controller in their power density, and may or may not be including their auxiliary power, depending on certainly not in terms of their volume. They should be including that in terms of their efficiency. And all of them, don't necessarily report their EMI results on how effective they are at passing those standards. And I'll note this plot keeps getting updated, right? This was, I'll say, an earlier work on the switch tank converter. It has since pushed its efficiency or its power density numbers up here closer to the Virginia Tech LLC. And likewise, this work has continued to push its production out as well. And we're starting to see other converters come in on this plot and be able to kind of put their pins in the ground, where hopefully we'll continue to see further advancement with all of these technologies where they push them out. So what are some common threads with these different designs, right? One that's noted is almost all of these are a fixed conversion ratio, right? There's the EPC Buck that does have the ability to provide regulation. But when it came to the switch capacitor converters and the LLC, all of those were operating at a fixed conversion ratio. Now the LLC obviously can operate off of fixed conversion ratio, but it really hasn't been optimized for that. And you would need more advanced control for that, so they really haven't factored that in. All of these work with resonant or quasi-resonant operation, right? So they're all trying to get this soft switching operation that allows them to reduce the losses on their switches and either use silicon switches such that we reduce the losses on the silicon switches, or use GaN switches and then be able to switch higher, which allows us to kind of reduce the volume of our passive components. All of these use a lot of switches, right? These are not just our two-switch solutions. Even the EPC one use multiple interleave stages. But what's also interesting is all of these, at least in terms of the academic ones here, use a 50% duty cycle operation, which means you're not taking a significant portion of your time with the switching transitions, right? This is kind of another shared interesting characteristic of these converters. What are some unique things? Well, we saw a really wide switching frequency range, right? We had the silicon converter that was at 100 kilohertz, up to the GaN converter that was all the way up to 1 megahertz. We had GaN and silicon solutions. Many of these have some very unique gate drive challenges, right? For the matrix, for the LLC, everything is your typical high side, low side type of converter. It's basically all half bridge technology. For many of the switch capacitor topologies, though, you actually need a more challenging gate drive solution to enable all of that conversion, and you need more isolation there to be able to hit there. We also saw isolation, right? If isolation is a requirement, then the LLC is going to meet that that demand. We're not going to see these other two be able to meet that very easily, right? They are inherently non-isolated. And then there's also this interesting part of scalability, right? So with many of the converters, the switch capacitor converters, we were already seeing how many of these are kind of interleaved, and so we can just continue to interleave these. With the LLC, you kind of have to interleave in these big blocks, right? You can't just naturally add on some, interleave more output stages on there without scaling your transformer as well, and that becomes very challenging. So both of these, all of these designs, I'll say, have kind of unique challenges when it comes to how they might scale to either higher voltages or how they might scale to higher power. So some conclusions here, right? We looked over some power density with both some LLC and some switch capacitor converters. We saw an LLC solution that I'd say has gone through a lot of iterations. It's very optimized. It has had a lot of different people looking at it. And I would say what we're going to see from it is likely incremental steps moving forward. On the switch capacitor converters, I would say these are very much ongoing research on what is even the best topology, right? Like we saw two pretty different designs that there's still some argument on which one of those is better. And maybe even those two solutions aren't actually the best switch capacitor topology when it comes to this type of application. And so we'll likely continue to see more work there, and we might see these more, I'll say, evolutionary leaps as opposed to this constant iteration that we saw on the LLC design. And I'll say the other thing we saw on this is comparing these converters is a challenge, right? We don't know if these are performing the exact same operations like we do in Google Little Box Challenge, or at the very least, there isn't this set of specs that all of these papers have agreed that we will hit these specs and then we will take our power density. They basically said, okay, it's a 48 to 12 volt application, or at least a 4 to 12 or 4 to 1 conversion ratio application, and we will design our targets around that. Whether they're actually regulating to the same voltage, whether they're all meeting the same EMI specs, is not something that's, I'll say, as much of a focus for these type of applications as we saw in Google Little Box. So that wraps up my presentation. Again, I'll thank Zichao for providing a lot of this, and obviously I've leveraged a lot of work from Virginia Tech and EPC in citing their figures here. But I'll go ahead and open it up for questions now. Or deafening silence.
So let me kick this deafening silence out, Andrew, and let me see if we can start up some question from the students as well. So one of the things I always think about when we compare these topologies and these different types of converters, Andrew, is how do we compare reliability? How do we compare that, okay, I get all of this at highest power density and highest efficiency. How long will it run? Will it run for 20 years, or because of the way we are trying to attack these topologies, it's going to die in 3 months because of whatever trade-offs we are doing? Is there a comparison which you have seen in these different variations of LLC versus SCC or GaN or silicon carbide or whatever it is? Have you seen any of those things, or what will be your comments on that from that perspective of lifetime of these converters?
Yeah, so lifetime is a good consideration, and all of these converters obviously look at a very high component count, right? We saw even on the LLC, which can be, you know, at its simplest form is basically 8 switches. Here it had multiple, you know, lots of switches on the output. Generally, it had switches in parallel, and so it gets up into, you know, closer to, I think, 20 switches. And then obviously we saw with both the switch capacitor topologies that they end up using a lot of switches as well. I'll say I look at it from a long-term perspective. Well, short-term right now, we know that GaN has some reliability issues, at least what we've seen shipping so far. But many of the GaN manufacturers have gotten to the point where they're qualified for automotive applications and, you know, those different aspects of it. So I will say their reliability is improving. And so at a certain point, I think we're going to have to say, okay, this is on par with silicon, right? Once all the manufacturing defects really are designed out, and once we get there, I don't think there's a fundamental reason why GaN would be less reliable than silicon. And in fact, many would argue it would be more reliable than silicon because of its temperature characteristics. When it comes to how do we look at these designs right now, I think one of the really interesting things to look at is the thermals, right? When it comes to a lot of mean time to failure and failure analysis, a lot of it comes down to thermal characteristics of the devices, right? And you can see a very strong correlation to the hotter these devices are running, the more failures we'll see. And there's some very well-known breakdown mechanisms in silicon as far as temperature. Many of the other components also have these very specific curves where it comes to temperature and the lifetime. And so from that standpoint, what some of these have shown is the temperature rises, right? They'll show what the operation looks like when they're operating at their peak power. And all of these converters are efficient enough that they don't need heat sinks, or at least they claim they don't need heat sinks, and they don't need air flowing across them, right? And so if we were to normalize all of these at a specific power level, and we were to normalize the airflow and everything else along those lines, what I think would be one of the very good indications of reliability would be those thermals, right? What is the hottest component? What is that delta T rise that we see in that? And that will give us a good indication, right? Some of these spread the heat out very well because they have lots of switches that are basically sharing the burden of the heat. And so we'll see a very even distribution of the heat. In other cases, there's just a few switches that end up taking a lot of the heat. And those, I think, naturally are the ones that are going to likely, statistically break down. So from that standpoint, the switch capacitor converters have a little bit of an edge because they tend to spread that heat out a little more evenly. At the same time, especially if we look at, say, the EPC Buck here, right? This has 5 interleaved stages, right? If one of those goes down and at least doesn't fail as a short, you could take one of that out and the rest of the converter will still operate. If you look at most of these other converters, if one switch goes down, the rest of the thing goes down. So these designs definitely are not a modular design, although obviously they could be at a certain point. The EPC design here, for example, does have that a little bit of modular capabilities. So it's, to kind of wind back, I think the thermals is very important, assuming that we get to a point where the GaN is on par with the silicon.
I completely agree with you, and I also I didn't thank you as well. The presentation was superb. Comparing, as you were saying, like all these converter topologies is extremely hard, and once you start looking at reliability or another metrics, I don't know whether there exists work out there which compares all these topologies from a reliability standpoint. But if there is something, I think that will be very interesting as well. Whether it is through the thermal, or you mentioned as having this single point of failure, how modular it is, but still also there are these failure mechanisms which can throw off these converters. It has to be very specific kind of failure. Okay, we hope that the switch doesn't fail short. There are like all ifs and buts there, which makes it very, very challenging and probably interesting as well to solve it as a problem. But overall, thanks for the presentation. I learned a lot of things from that.
Any other questions?
Let me ask one more question, Andrew. This has been bothering me for last probably 3 years. I tried this on Robert, so let me see if I can get a flavor from you. So the question is, if I have seen that slide for a long time where you compare the capacitor energy storage density with magnetics. Is there a fundamental reason for that? Can I say that from physics perspective? Oh, this is the reason why capacitors are more energy storage or energy dense. I don't know, so I cannot
say it from a physics standpoint. And really what we're comparing here are devices that are in a certain class of power rating, right? So these are the type of inductors and the type of capacitors that we would typically use in a converter that is, say, less than 2 kilowatts or something along those lines, right? So relatively, inductors that are on the order of up to, I'll say 10 amps up to, tens of amps. And we're looking at capacitors that are on voltages up to, say, hundreds of volts. As we scale down in this space, fundamentally, it kind of comes down to a case where these capacitors are kind of these 2D devices, right? We're really just looking at the dielectric, how good the dielectric is, how short or how close we can get those plates and still stand off that voltage, and then how we can cram them into a nice small package. The inductor ends up being a little bit more of a 3D device, right? We've got a core and we've got flux that has to complete the loop. And similarly, we have to worry about saturation of the materials and everything else along those lines. So basically, it just comes down to the geometries of the devices we can build, the dielectrics and the materials that we have for the inductors, and the nature of these devices in this space. I think Dr. Krein just pointed out that once you actually scale up to a larger size, what we'll typically see is actually the reverse. We'll see that the inductors can actually have higher power density once you scale up to maybe the megawatt scale when you compare that to capacitors, and you have to stand off higher voltages. So it's not a universal physics thing where you could derive that. And in fact, this was one of my qualifying exam questions, which we had an interesting discussion about, and the answer is I don't know at that time. But basically what it comes down to is that we don't have, in this class of device, we see this trend and we work with these class of devices. But from a physics standpoint, there's no, aha, this is what the answer is. It's because when you actually go to build something, these are the limitations you run into. And it's also very difficult because research is looking at more power inductors that do have higher power energy density per area, but they're looking at it on a very small scale. And maybe they're looking at some of these racetrack inductors or different things that you'll see for on-chip inductors. But this also doesn't really capture the quality of these capacitors or these inductors either, right? When it comes to their, their ESR and everything else along those lines. So it is a challenge, right? Like this is in some ways misleading because we know that you're rarely going to be able to use all the energy out of the capacitor, and you're rarely going to use all the energy in the inductor. But at least this points us in the direction of, okay, if I have a trade-off, maybe there are some gains to be had.
I see that. The reason I keep asking this is that it's so distinct difference here. You can see orders of magnitude. It makes begs a question like, okay, is there a physics limitation? Why it is? Or maybe there is also a possibility, and I don't know whether that's a true or a false statement, what I'm going to make, is do you think that people have worked on making these capacitors better than the people who are working on the inductors per se, where they're thinking about, okay, let's make an energy dense inductor. How do I structure it? Okay, if it's a volume, if it's not a physics problem, is there a better structure of inductors which can increase the volume density or energy storage density of inductors?
I get, so it's a valid question, right? And there very well could be a case where sometime early on, something drove a lot of research into the capacitors and the inductors. It wasn't necessarily that these capacitors were designed for power electronics, they were designed for something else, and it turns out they're really good for power electronics. Whereas in the inductors, right, you don't, outside of power electronics, you're not really getting those used in a lot of cases. So it's completely possible that it is a R&D investment that has driven a lot of this. My guess is it's more of the materials, right? If you have a dielectric that has a high withstand voltage, is really thin, and has a high dielectric constant, right, you can make a really good capacitor. And when it comes down to the inductors, right, we need something that doesn't saturate and has really low losses, and we don't have that aspect of it. At the same time, we have to pass a lot of current through these wires, and that is naturally a lossy mechanism, a lossy energy storage mechanism. And so there's, if we really want to increase the energy storage, we have to do that in the current, which means we need thicker wires as well, or at least wires that can carry that current.
Yeah, I see that, Andrew. And this is where it again becomes mind-boggling to me. When we look at electromechanical energy conversion, everything is through inductive. What happens with energy storage that capacitor becomes better, or storing energy in the electric field becomes better than magnetic field? Whereas when we look at energy conversion, magnetic field becomes better. So anyway, I think I don't want to drag this, but I think
yeah, that's a fun conversation to have with Dan Ludos at Wisconsin, right? Right.
I'm sure he will say, "Oh, it's all electrostatic. That's all what matters. Electromagnetics. We have been doing it wrong for centuries."
He wouldn't say that, but he would definitely. So for context, Professor Ludas at Wisconsin has spent several years working on basically these electrostatic motors. So we like to joke that, you know, we're working on these capacitive-based power converters. He's working on these capacitive-based motors. Let's have a switch capacitor driving his capacitive-based motor and get rid of all the inductors out of this this equation. But yeah, he's doing some very interesting work. It's got some interesting parallels to this type of operation, but I'll say it is different. But yes, some of it does come down to those physics of you know, the permeability and those different pieces like that. It's also interesting to compare that to wireless power transfer, right? Where we have most of it is this inductive wireless power transfer, but we also have some capacitive wireless transfer, wireless power transfer research being done as well. And there you very much are working with physics.
Any other question? Maybe I asked all the question, Andrew, for you, and I dragged it to 4 o'clock, but sorry, guys.
All right, if that's all, thank you, everyone.